Welcome to Tic-Tac-Toe the Hard Way, the podcast in which a writer and a software engineer train an AI to play a simple game.
And take a hands-on approach to exploring the very human choices that go into training a machine learning system.
Hello, David.
Hi, Yannick.
Here we are again.
It's the big day.
Yeah, Tic-Tac-Toe.
Yep, I got my prize-fighting robe on.
Excellent, excellent. Glad to see you came prepared.
And I'm looking forward to taking home the big gold belt or big gold cup or something, whatever it is.
I believe that's what I've heard. Gold is pretty popular in the Tic-Tac-Toe world. To remind folks, we're back to talk about how training our Tic-Tac-Toe agents went. And, last time we talked a bit about data generation for that. And now I want to just talk about how that went.
And I think we should point out we are going to set our models against each other.
Yes, we are. Oh, yeah. I'm ready to throw down.
It all comes down to this.
So I guess, but before we get to that, we have to talk about how did we get those models in the first place? And for me, I would say in terms of talking about the actual training, I would say it mostly went relatively straightforwardly. Though I was able to have some fun with it that I'll elaborate on. But it generally went pretty straightforwardly. And in terms of human decisions and things that I could have changed, it's actually mostly a story of not changing things. So in my scheme, the main lever I have to change things are the rewards. So what is the reward given for winning or disqualification or losing or that kind of thing? And in this case, I didn't actually change any of that. I just left it the same and it worked out well enough. So I sort of kept that the same. But I was able to experiment a bit with a training regimen that I'm going to tell you about. And I'll sort of break it down into the steps. So step one was I took my Tic-Tac-Toe agent and during training, trained it against a random agent. So one making random moves and sort of let it do its thing, very similar to Tic-Tac-Toe. And it learned and it did pretty well. So it would get a win rate in about the 90% range.
That's pretty good.
Yeah, pretty decent. So it was doing pretty well against random. And then I had a thought, what if I could train it against a better opponent? In fact, what if I could train it against the agent that I had just trained? So that's what I did.
You trained one and then you're going to train it again against
the first one.
The first one.
Yeah, I'm going to train a new model. And during its training, the opponent it will actually face is the one that got trained in the first round that was played against random.
If that works, is there any reason not to just keep on doing that until you have the world's mightiest reinforcement learned tic-tac-toe player ever created?
Presumably not, other than maybe other things I want to achieve in life. But yeah, it could just keep going.
AlphaGo, the deep learning system that learned to play the game of Go, in its second iteration, it played itself, as I recall.
Mm-hmm.
And
yeah.
It was already beating the best human players, and it incredibly quickly became a far better player, which is, I guess, predictable and weird at the same time.
Yeah, I thought it was pretty cool. I wanted to experiment a bit with that self-play on a very small scale and see if it would make a difference. So that's what I did. So I essentially trained a second generation of Tic-Tac-Toe agent against my first generation of Tic-Tac-Toe agent. And it's still played pretty well against a random agent. So my second generation agent could still beat a random agent at about 90% win rate. But it could also beat my previously trained agent. So generation 2 could beat generation 1 with about an 83% win rate.
How significantly did it boost its win rate against the random player?
Against random, it didn't change all that much. It was still in the 90s. So it didn't change too much against a random agent.
But it's doing really well against an agent that has a little sense in its head, so to speak.
Exactly. It's sort of gotten to see that agent in play and learn to do well against it, which I thought was really cool to see.
I was not expecting a second generation from you, Yannick.
Well, I told her I came to throw down, so.
Because I failed at doing my upgraded version.
Ooh.
Which will...
So tell me a bit about your journey. So that's essentially sort of the little story I wanted to tell, and that sort of left me with the agent that I have to pit against yours, and that's how I got there. But tell me a bit about how you got along.
Yeah, well, now I'm getting a little nervous about this match. I thought I had it in the bag, but now I'm not so sure.
Yes, you should be.
So once I had gotten through the boring and meaningless problems of generating games, and not all that process is boring and meaningless, just the part where I'm not doing JavaScript very well. So I finally had data that looked legitimate. And so I started training a model on it. And it didn't go particularly well. I was training it on 50 epochs, which are sort of loops, having how many loops it takes back through the training data. I know that's pretty rough, but that's, rough is okay. And it just seemed to stop learning very early and not learn particularly well. It definitely was learning, but just not very well. The results were poor. So you suggested that maybe I wasn't training it long enough. Instead of 50, try 300 or 500 or 600. And sure enough, it just was. It took longer, but it did start to pick up and train itself better. But we also discovered yet another data problem, which we then fixed.
Yeah, and that allowed us to bring the epochs back down to something that could train a bit faster.
Yes, which is helpful. I did find at one point, even with the corrected data, that my results playing against a random opponent, I tried training it for 500 epochs after everything was fixed, just to see what would happen. And I was excited because the accuracy during the training loops kept increasing, which generally, is a good thing.
Mhm.
And the loss function crept down as well. But when I played it against a random player, it actually did worse than some of the models that were trained on fewer epochs, on 100 epochs. Yeah, and beats me why that's the case. But
I think to me that sounds like more of a case of overfitting. So going back to that terminology, you've trained it and it's trained for longer and it's gotten better at the training data, but not as good at generalizing into what it will actually experience when playing in a free world with a random agent in the viewer. So it was getting better at the training data, but it was probably getting so narrowly focused on that it would do worse in general situations.
entirely possible. I mean, its accuracy was getting into the mid 90% accuracy.
Overall, how are you able to do against the random agent?
Okay, it certainly beat random. Somewhere in the upper 60s, maybe, percent of the time,
Okay.
which is not fantastic, but it had learned something.
Mm-hmm. And that was the 500 epoch thing or the shorter training?
That was the shorter. The training it more dropped at 5-10%.
Okay.
It turns out one of the things I was worried about was that Tic-Tac-Toe would not be complex enough to warrant all of this, that we would succeed at it too easily, because there's really only 3 important things you need to know in order to win Tic-Tac-Toe. And it turns out it's actually probably fairly complex. So that's good. I mean, it's good for an example anyway.
Interesting. Yeah. Cool. All right. So any other experiences while training, or that sort of pretty much led you to the model we have today?
That's pretty much what led me to the model.
Okay. So now the great battle.
Yeah, I guess.
Yeah.
Yeah,
Okay, so
I'm
that
confident. I am not concerned about this at all. Not one tiny bit. So how many rounds are we going to go here? How many games?
We're going to go 500 rounds. And for listeners at home, a bit of a difference from last time. Since we're sheltering in place due to a pandemic, we're each going to load these up on our machines at home and see how they do rather than sort of looking over each other's shoulder. And then I'll share the results and we can go from there.
It should take something like 20 seconds around that.
Yeah, something like that. So let's load it up.
Okay, hold on.
Okay. Mine's going.
And it is surging behind magnificently. Oh my, go! It's not going.
Getting the full live commentary. I am calmer and more at peace with the results I'm seeing.
As in life.
If that gives you a preview as to what to expect when this is done. Oh,
okay.
Are you,
Yeah.
Is yours done?
I am done, and I would just like to set a new floor for expectation, okay? If I can win any games against a professional developer who has not only trained his game using reinforcement learning, but then has used that intelligence that he created to train it again, so it's like trained squared. If I can score a single win, then I think I am the victor. So how'd we do?
Indeed. It's great. It's a great attitude to have coming into what I'm about to read.
Yeah, go ahead.
Perfect. Because then we both go home happy or stay home happy. So I will say you did win. You did win some
Woo!
games. And more than one. You won 18.8% of the games. And this is 500 games in this run. 18.8%. That's almost 19%.
Which is almost 20%, which is about 100 games under my belt.
Yeah.
Okay. That is
That's
amazing.
fantastic.
Okay, we can stop right there. We can stop right
It's
there. That's
amazing.
fine. Go ahead.
Okay.
Go ahead.
So that leaves me winning about 78.8%.
Which rounds
of the
down
time.
to about 40%.
You know, in some rounding systems, yes.
In base 2.
in decimal, it rounds up
okay,
to
fine.
79%. So that was pretty good. We tied about 1.4% of the time. So not too many ties. And disqualifications, your agent got disqualified in 5 games total. So that's about 1% of the games. It did something illegal. Mine did not. It got lucky, maybe.
Okay, so aside from my moral victory, there are a couple things that are really interesting to me about these. And there's a lot that's really interesting to me. One is I'm impressed and surprised that it didn't tie very often. In normal tic-tac-toe, I would expect more ties. I'm not sure why, or that that's accurate. But not tying, I don't know what to make of that.
I guess it means one is dramatically better than the other. I would say in evenly matched tic-tac-toe, you'd expect a lot of ties.
Okay, I'm really sorry I brought that up. That makes complete sense. And then on disqualifications, which have been a problem for my model throughout the process. A disqualification basically is when my model tries to play a mark in a square that already has an owner or whatever. Or maybe it's trying to play a 4th mark. And so that number had been disturbingly high. It turned out to be bugs in the data. A lot of that turned out to be bugs in the data. I guess I'm encouraged that the thing learned what we would call the rules of tic-tac-toe pretty effectively.
Pretty effectively, yeah. That's a very low disqualification rate, so.
Yeah, so I will sum up my model as follows. It knows the rules, but it's not very smart. It's like me playing chess.
Better you say it than I. But yeah, I think that's good. It's not doing illegal things, which is an important part of the learning process. It's managed to capture that pretty well. And it wins some games.
Yeah, 100.
Yeah, exactly.
Imagine if it went for a full minute or a day or a year. It'd be tens of thousands of games.
Percentages would be the same, but yes. So yeah, it's definitely learned something, and that's something to be very proud of.
I am so proud.
I am proud of you.
Well, I'm proud of you too. I actually love the fact that you played your game against itself.
Yeah, I was like, I'm going to go as all in as I can, even for this.
Can I tell you how I tried to go all in, do the equivalent, take it to the next level, if you will, which I failed at?
Yeah, tell me about other experiments you did.
The main thing was trying to have it when my system is going to generate a game and generate a move in a game. I wanted it to look at the board and see if there is a preference among squares rather than just always randomly choosing a square, where the preference would be first, if it sees that if it puts down a mark for the player it's currently playing as in a square, it will win the game. It's just one mark short of it. The second is to look to see if that's not true, look to see if it's threatened by the opponent winning in the next move and then blocking that. And I spent a long time trying to get that to work, including by looking for double plays. If the player that is currently making the move has a double to play, then it should look at not just, is there a single mark that would win the game, but is there some combination of 2 marks that would? Looking up doubles took way too long for me, and not for interesting reasons. It's just a set of nested loops, and there's stuff about cloning arrays, and it just got really annoying and hairy, and I wasn't going to succeed at it. It was basically, I wrote a very successful bug generator, is essentially what I did. So then I figured, well, okay, so I'll just look for one move. So it won't work with doubles, but that's fine. That still should boost. And I was on the verge of just getting the programming right for that. But there were some annoying, pernicious bugs just in my JavaScript, and I couldn't get it done in time. But I assumed that would have helped the system to play better.
Yeah, essentially, there you're describing generating better data, sort of somewhat smarter data than random that it can learn from. And that would probably help. I could talk a little bit more about some of the other difference that sort of separate these two things and give you some other things I think my agent performs better. That might make you feel better, may not.
Unlikely to make me feel better, but I will have learned something. So go ahead.
In some ways, the algorithm I picked, the reinforcement learning scheme, is somewhat better suited to this kind of problem of long-term reward modeling. It's sort of geared towards that kind of thing of considering the game as a game and figuring out how to go from the end state, did you win, lose, get disqualified, to what are the things along the way in order to make the wins happen. So it's designed in some ways to handle this kind of problem a bit better than the sort of straightforward supervised learning approach you were taking. So that's one general difference in the two, and why sort of for certain classes of problems, different training schemes are useful. Now, I should say it's not that supervised learning at all can't do this. There are a couple of other things in your setup that maybe made it somewhat challenging. I know one thing from previous sort of debugging exercises is that I know your agent struggles a bit with doubles. That's actually where all of the disqualifications happen. And it's partly because your data has some class imbalances that aren't dealt with. And what I mean by that is there are a lot more single moves than double moves by an order of magnitude. And there are ways to deal with that computationally in how a model is coded and errors are weighted, but it's kind of a bit more advanced than we could do here. But there's literature in how to sort of deal with imbalanced classes where you have one type of thing that happens way less frequently than the others.
Doubles are, by rule, once a game for each player.
Exactly.
I have heard that this sort of class imbalance can be much, much more serious than playing tic-tac-toe when, for example, you're dealing with a population in which some significant and important portion of that population is underrepresented.
Mm-hmm.
For example, this shows up in some ways in which models and machine learning can fail when dealing with race, when one race is a much smaller percentage of the population.
Yeah, I guess, class imbalance could be a part of that problem. There could be many things that lead to that being an issue, but unrepresentative data is definitely a contributing factor to that kind of problem.
Can I say something about, if I go back to the way in which I was trying to come up with a second generation training by generating data that was looking for an opportunity to win at each move? One of the things that I think this is one of many examples of the difference between thinking about machine learning as you pour in the data and you see what happens, and what actually goes on in building a system, which is very frequently somebody trying to, in this case, to have it be a little bit smarter by putting in a rule that is based upon human intelligence.
Yeah. That's the human sort of strategy for how to train this thing. And for me, it was that scheme of like, okay, let me try and train it again against the previous thing. Like that's that human, whether intuition or heuristic about how can we get it to do the thing we want it to do. And it's something that has to be thought of carefully in order to get it to work.
I don't know the answer to this question for sure. I'm not sure it's answerable, but you'll tell me. We agree that it's likely that if I had been able to institute into the training set the idea that always look to see if there's a winning move rather than always just go randomly, that my model probably would have performed better. Do we think that if my data were better and there were more of it, that the system would have figured that out on its own, figured out to take the first opportunity to end the game?
I think we'd have to know by experimentation also, but I'm not entirely sure what you mean by learn on its own.
Would it learn it from data that had not been generated with the rule look for a winning move? Purely random data.
But that's the data you have now.
It is. But if there were more of it.
If there are more of it.
Yeah.
I guess what I would say is I don't know if just having more of the same data would help. But another technique which I would suggest in sort of trying to improve this problem is adjusting the model a little bit. So one thing we talked a bit about early is whether it matters or not, whether it knows that this is in a game, whether it knows that like moves are a thing in a sequence that make up a game. And I said early on, like, doesn't matter too much. That was a bit of a simplifying assumption. That is probably the next thing I'd look to change, because there are supervised learning schemes that can take into account the sequential nature of the game, that move 2 follows move 1, and so on and so forth. They do require a bit more experience and comfort with sort of machine learning programming, and also it changes how the data is shaped. So even if it's random, that sequential aspect may help it learn those kinds of things more than just having more of it, is probably the approach I'd take for that.
Once again, human decisions are shaping this stuff.
Yeah, there's a lot of that engineering that goes into creating a system that's going to be able to do the task we want to do.
You know, I'm winning 300 games a minute at this point. I don't really feel the need to pile on by improving it. I do have what maybe one last question for today, which is outside of the realm of developers. People talk about algorithms, and they have, I think, associated machine learning with algorithms. And anything that goes wrong with machine learning, it's giving outcomes that we don't want for one reason or another. People will say, well, we need to know what the algorithm is. In this very, very simple case of supervised learning, there is something called an algorithm. When you as a professional are talking about the algorithms, what are you and your cohort referring to? Because I think it doesn't quite match up or cover with how the term is being taken more broadly.
I don't know if I have a precise answer to that, other than we maybe speak of it with a bit more precision. We speak of specific algorithms, things like gradient descent or other kinds of things that refer to specific steps that a computer is going to execute to do something. Now, maybe as part of developing a program or a system, a human is going to make a bunch of decisions and going to do a bunch of, like the programming itself, that's a bunch of decisions a human or many humans are going to make. I don't know if we would typically call that part of the algorithm. In sort of the computer science definition, we are really talking about the instructions for the computer, not the how did we get the instructions for the computer. So that's how I think of the term.
So when people ask for algorithmic transparency, or they talk about what the algorithms are doing to us positively, but usually when people are talking about this, they're talking about things that are worrying them. They are not distinguishing between the algorithm in the technical sense, and frequently I think they're not thinking about the role of data, which may be really what the issue is. I think it's just become a really broad term for the stuff that machine learning does. Nothing wrong with that. You know, language is language.
Well, that actually sort of suggests a thing we'll be able to talk a little bit about more next time, not just algorithms, but we can talk a bit more about what kinds of patterns we saw our agents playing. So we talked about sort of overall statistics, but we can dive a little bit into the kinds of things we see them doing. And yeah, some other topics next time.
Did the systems learn to have a favorite square to play?
Yeah, that kind of thing.
So that should be really, really interesting.
Indeed.
Okay.
All right.
I'm going to say good job to you.
Thank you.
As a fellow winner, I want to congratulate you.
And I congratulate you.
Okay.
You fought through a lot of bugs, so you're still here. And that's something to be quite proud of.
I'm still standing.
All right. Talk to you next time.
So long.
You've been listening to Tic-Tac-Toe the Hard Way with your hosts, Yannick and David Weinberger. This is a production of Google Pair, with thanks to Rebecca Salois, Eric Johansson, mixer and editor Brian Gordon,
and the entire Pair team of developers, researchers, designers, artists, philosophers, and more. A special thanks to Nikhil Thorat, who created the music with help from AI by Google Magenta.
You can find links to code and more in the show notes and at our website, pair.withgoogle.com/thehardway. Once again, that's pair.withgoogle.com/thehardway.